Good morning. I'm Hussain, former professor, Department of Chemistry, University of Dhaka. We are arranging a lecture series on X-ray crystallography and solid-state chemistry. This is the 18th lecture on X-ray single crystal diffraction. We'll go to the next slide. We are talking about crystal, and we said that ideal crystal. What is the ideal crystal then? An ideal crystal is a periodic array of structural units. And what is structural unit? Such as atoms, ions, and molecules. These are the structural unit. So when this structural unit is infinitely repeated in 3 dimensions, or structural units in space, we call it a ideal crystal. The structure we have described the structure in terms of lattice. And we also mentioned that we can suppose that atoms are each lattice points, or ions in each lattice point, or molecules in each lattice point. This is the basis of crystallographic theoretical, or I would say fundamental crystallography. But then it's very rare we can get ideal crystal in nature, very, very rare. So we have to prepare a reasonably good crystal for starting the 3-dimensional structure. And what do we mean by reasonable good crystals? There are a large number of monographs, book chapters, research papers on how to grow crystals. This is itself is a field, I would say, and it is very, you have to have very good patience in preparing a good single crystal. Okay, many researchers with trial and error methods, they do find out their own method for growing a crystal to determine the structure 3-dimensionally. We can prepare crystal of almost all types of methods, such as, let's say, alloys and inorganic, organic, and biological compounds. As a result, crystal growing is a very, very wide methods, and it depends on the thermodynamic and kinetic properties of the system in interest. Okay, next slide. What we do then we have to choose a single crystal for 3D structure determination. And how to choose the crystals? There are 2 main points we have to look into it. It must possess uniform internal structure. Crystal must possess it. And proper size and shape. So the first requirement, that is, it must be pure at the molecular, ionic, or atomic level. And the crystal should be, as we are going to determine 3-dimensional structure, crystal should be a single crystal. What do you mean by single crystal? When we prepare, we will see that crystals are getting 2 in and composed of subcrystal. So crystal should not be grossly fractured, bent, or physically distorted. That's what we have to remember very much. Okay, then we will see that almost all single crystals composed of misaligned minute region, and that minute region we call mosaic blocks. Why? It is also a desirable thing, because a misaligned minute mosaic block will give you a better intensity than that of pure or ideal crystals. So we need a little bit of misaligned misalignment in the crystal we prepare. And that misalignment is a very small misalignment, which is around 0.1 to 0.2 degree. You can see that's what we call mosaic, and here there you can see that it's a misaligned, a little bit of misaligned things. So another thing, we have to choose a crystal size properly. So we have very many methods. We do take it photographically, the intensity we collect of reciprocal lattice points, or we can collect it by diffractometer. So when we go for a commercial diffractometer, the primary beam's dimension is 0.5 millimeter and 0.5 millimeter, a bit larger. So single crystal we prepare should not have more than this size. But it is said the preferred crystal should be 0.1 to 0.3 millimeter size. So that's what we also have to consider. And then another factor we have to consider, we know the crystal absorbs X-ray. So absorption process should be minimized as low as we can have the absorption process. Otherwise, our intensity will reduce. So to reduce this error, absorption process, two parts are considered. One is this, that we have to have more penetrating radiation. And in this case, molybdenum K alpha is the radiation we choose. Shape of crystals, also we have to take care of it. And then shape of crystal, so we have to make it in such a way that the all reflections, reciprocal reflections, real reflections, that have uniform absorption, or that this depends only on theta. So these are the pre-requirement before we take data collection, go for collection. Now we have to see how our crystal, what are the method by which we choose crystal and fix crystal. And they say mounting crystal is also a art, I would say. So we need goniometer head. What is goniometer head? Here you see a goniometer head. So a standard goniometer head has got A and B, which allow the crystal to tip about plus minus 20 degrees centigrade, two arcs, and then two sledges, C and D, which allow the central axis of the head properly shifting. So the head is designed to screwed onto a rotating spindle in the camera, and the crystal can be aligned so that either a direct or a reciprocal crystal axis is in axis of rotation. How do you pick the crystal? You see, here is a mounted crystal, and in this we use fine fiberglass of about 20 to 70 micrometer size, and then that fiberglass is fastened in sealing wax. And why do we fasten it? You fasten it in a metal pin, which is about 1/8 inch size, usually made of brass. And there are different types of materials we use as wax, but a very good one is epoxy glue, by which we adhere our crystal in the brass pin. And then we have to now align this crystal, which we have picked up in the goniometer head. So there are methods of alignment of crystals. One can use just simple microscope or an optical alignment goniometer, optical aligned goniometer. So this has got a rotating circle here, A, and also a base, B. So almost the properties of crystal, if we use optical examination to see the crystals and its properties, but this is another field of study and which is not in this syllabus, and therefore we skip that. But this is a very important field of study for crystals and its properties. Okay, so very important instrument that is very crystal form two circle goniometer, optical goniometer, two-circle optical goniometer. A light source is there, a crystal support is there, and a combination of microscope and telescope is there. So when we study with the use of this one, we can align a crystal. Here is, you can see this here is a line, very much aligned crystal by this using the optical alignment system. This crystal, you see, it's a little bit misaligned. And if we rotate this, you can see that it's 180 rotation misalignment is there too. So, of many properties of crystal study, the optical goniometer is being used to collect three-dimensional X-ray crystal data. We also use optical goniometer, as I said, and then we see by optical goniometer it's always possible to see which one is a good crystal, and we can do it using optical goniometer very rapidly after a little bit practice. The result with a very with a poor crystal, a precise alignment is plus minus 0.1 to 0.2 degree, which is most acceptable for three-dimensional structure determination. Now data collection. We have now crystal mounting. We are mounted it in a goniometer head and also in the X-ray X-ray equipment. Now we have to collect data, and there are very many techniques we use for collecting data, and these problems are two problems we have to address. One is geometry of diffraction. We calculate from which is size, shape, symmetry, direct and reciprocal lattice can be calculated. Another is the observed intensity. From that intensity, what we related, the distribution of diffracting electrons in the unit cell. Okay, so if we take into consideration, we will see that till 1960s, we used photographic film method. But after 1960, there is a trend that photographic film method has been replaced by automatic diffractometers. Well, of course, automatic diffractometers gives you a quick data collection, but there are problems also there. Problem is that if you do not identify properly the unit cell and lattice type, there you will come into error, and that will be a that will be not good collection, and your end result will be your structure determination is not accurate. So yet these photographic methods are excellent tools to work for, because this is specifically used in teaching crystallography, and that can never be replaced by other method. I would say young scientists who are interested to learn crystallography, they should go for practicing photographic methods and learn the basic crystallography first before taking this three-dimensional data and solving the structure. I said here, a number of errors have been found recently in space group and lattice assignment. And we think that this error is due to the dependence on individual reflections found by automatic diffractometers. So here I have to say that we have to be very careful in collecting data, looking into geometric diffraction, and also observed intensity, as well as a basic knowledge of crystallography. Okay. We have been seeing that there are a large number of cameras to take reciprocal lattice photograph, but main two are Weisenbach photograph and Barger precision camera. Okay, we go to that now. Well, here is a camera, Weisenbach camera, which has been developed in 1924 by Karl Weisenbach, a German scientist. And well, many years with this camera served to take data collection in X-ray crystallography many years. And as I said, that nowadays it is supplanted by diffractometers in modern practice. Okay, that what is the main feature of this camera? There are 4 parts. A fixed base. There is a fixed base A, which is a schematic diagram of Weisenbach camera. You can see this X-ray is coming. Here is the crystal. It's stir the crystal and you get the reflected data in the camera, or a film is there, and then we record this reflection intensity and in the film, and then develop it, dry it, wash it, dry it, and we start analyzing it. And it has got a B, a movable disk, you see. And this one is a B, a movable disk. This is a movable disk. And the mobile disk translate to one side by means of crane is cool. We can translate it side to side. Okay, a motor, we do have a motor. This is over there, motor. This is the motor. We do have a motor here, and this motor will rotate. Gear train, cassette guides, and crystal mount. See in figure. So this is in the figure C. And then we have a film holder D, which is here is a film holder. This one is a film holder. What is the schematic diagram of the Weisenbach camera? Okay, there is a split knot which engaged, and then this can drive the camera back and forth by thread and shaft linking of the motor. When we took rotation photograph, then we disengage this knot, and therefore the film holder will be in one position, locked in one position. Okay, in the bottom we can see a commercial Weisenbach camera. And I say that there are many different types of camera for commercial, but I just show one here. And then now we have now collected data. So we can take rotation in Weisenbach photographs. Here is an example of rotation in Weisenbach photograph. You can see this is the layer. This is the layer. That what shows, this is a very parallel one after another parallel. There is no misalignment. That what is show that the crystal has been properly aligned, exactly properly aligned, and that crystal could be taken for 3-dimensional data collection. Okay, and then what we do get from rotation and oscillation photographs, we do get that is the crystal aligned or not? So we use this photograph to align crystals. We use this photograph to measure the cell ages along the axis of rotation. We use this photograph to find out preliminary symmetry information. And thus it is more easier, or even we can use precision camera for symmetry of information and cell ages. I'll come to it. Weisenbach photograph, what is the disadvantage of it? That 2-dimensional reciprocal lattice plane is condensed to 1-dimensional layer line. Indexing reflection is very tedious job then. Many photographs are to be recorded and avoid this overlap of spots. Well, therefore, it's desirable to be taking photograph a single reciprocal lattice plane mapped onto a entire sheet of film. And that what is here. You can see it is a Weisenbach photograph. for a single layer. And this method was first, as I said, it was developed in 1924. The technique is rather simple. A single layer line is selected by a slot screen that stops all other diffracted beams of the crystal when it is rotated. The film is then moved past and the slot of reflection that occur at different times and are recorded at different points. With this, I will finish the lecture because I said that this will take few lectures to complete the syllabus as well as to give I would say a very good basic knowledge how to work with Weisenberg photographs or rotation oscillation photographs, or even how we take data from diffractometer and this sort of things. A bit detailed discussion is needed. Thank you for this lecture, and we will continue in the next lecture about how we collect the data by photographic method and also by automatic diffractometer. Thank